Hello friends, welcome you all to the 54th lecture on functional analysis and its applications. In this lecture, we will discuss the sublinear functional and generalized Hahn-Banach theorem. These are the contents of today's lecture: sublinear functional and generalized Hahn-Banach theorem. Sublinear functional. Let L be a linear space, a mapping P such that L to R is called a sublinear functional on L if it satisfies the following two properties. First, P of x plus y less or equal to Px plus Py for all xy belonging to L. Second, P of alpha x equal to alpha px provided alpha greater or equal to 0, that is alpha is non-negative. Okay. The property first is called subadditivity and second is the positive homogeneity. For example, let L is equal to Rn if x is equal to x1, x2 and so on xn belonging to Rn. Let us define Px is equal to summation I is equal to 1 to n mod xi, that is mod x1 plus mod x2 plus and so on mod xn. Then P is a sublinear functional on L. Okay. So these two conditions satisfied. Okay. If in addition P satisfies the condition Px greater or equal to 0. Okay. So in addition of the definition, here if Px greater or equal to 0 for all x belonging to n, P is called convex functional. A convex functional P is said to be a symmetric if we have P alpha x equal to mod alpha Px for all scalars alpha. Okay. So for convex functional, here P alpha x equal to mod alpha Px in the place of this. Generalized Hahn-Banach theorem. Let L be a real linear space, not necessarily normed, and let P be a sublinear functional on L, that is P is a mapping from L into R satisfying the condition P of x plus y are equal to P of x plus P of y, and P alpha x is equal to alpha Px for all x belonging to L and alpha greater or equal to 0. If f is a real linear functional defined on the linear subspace M. Okay. Suppose here L and this is subspace M. For this is F. Okay. And P for this space. Such that fx less or equal to px. Okay. Then f can be extended to a real functional f0 defined on the whole space L such that f0x less or equal to px for all x belonging to L. And if L is complex linear space, then condition 1 is the same. Okay, this will be same, but second condition P of alpha x equal to mod alpha into Px for all x belonging to L and all scalars alpha. If f is a complex linear functional defined on subspace M such that mod fx less or equal to px for all x belonging to M, then f can be extended to a complex linear functional f0 defined on whole space L such that mod f0x less or equal to px. In this real case, f0x less or equal to px, but in complex case, mod f0x less or equal to px. Let us prove it. Case first. First, let L be a real linear space. If x0 not belonging to M, that is x0 belonging to L minus M. Okay, that is, this is L and this is M subspace. So here x0 not belonging to M, that is x0 belonging to L minus M. Suppose here x0. Okay, this one, and x belonging to M. X. If x0 not belonging to M, that is x0 is the element of L minus M. Consider the subspace M0, okay, for this, including point x0. So consider the subspace M0 equal to M union x0, singleton set x0. That is, here x belonging to M and x0 belonging to L minus M. So the span can be written as like this: x plus alpha x0 such that x belonging to M and alpha be real. Okay, this is the span by M and x0. Define f0 on m0. Okay, for this by f0 x plus alpha x0 equal to, here f0 is real linear functional. Okay, so this can be written as f0x plus, this is f0x plus alpha f0 x0. Okay, because f0 is real linear functional. Okay, here x belonging to M, so f0x is fx and alpha r0, where r0 is equal to f0 x0 is any real number, so that f0 is real valued. Okay, it is easy to see that f0 is linear on m0. Such type of case already discussed in the theorem of Hahn-Banach theorem. Okay, so it is easy to see that f0 is linear on m0 and f0 is equal to f on m. Okay, so f0 on m is f. If x1, x2 are any vectors in M, then f of x2 minus f of x1 equal to f of x2 minus x1. Okay, we can write because f is real functional. Okay, so as per the hypothesis of theorem, fx less or equal to px. Okay, so we can write this: f of x2 minus x1 less or equal to p of x2 minus x1. Okay, so this can be written as x2 plus x0 minus x1 plus x0. Okay, we have added and subtracted x0. Okay, so we can write this again by equation 1. P of x plus y less or equal to px plus py. So we can write this as P of x2 plus x0 plus P of minus x1 plus x0. Okay. So that minus f of x1 minus P of minus x1 minus x0, this part. Okay, minus f of x2 plus P of x2 plus x0. Since the inequality holds for arbitrary x1, x2 belonging to M, we conclude that supremum of minus fy minus P of minus y minus x0 less or equal to infimum of minus fy plus P of y plus x0 for y belonging to M. Okay. Choose R0 to be any real number such that supremum y belonging to M minus f of y minus P of minus y minus x0 less or equal to R0 less or equal to infimum of y plus M minus fy plus P of y plus x0. Okay. Suppose any R0 lies between these two. Okay. It follows that minus fy, this case left hand side, minus fy minus P of minus y minus x0 less or equal to R0 less or equal to minus fy plus P of y plus x0 for all y belonging to M. Okay. With this choice of R0, we shall show that f0x less or equal to px for all x belonging to M0. Okay. Let omega is equal to x plus alpha x0 be an arbitrary element in M0. Here x plus alpha x0 is W. If alpha is equal to 0, then f0 omega is equal to f of x and f of x less or equal to px. Okay, because already given fx less or equal to px for all x belonging to M. Okay, if alpha is equal to 0, that is the case of M. Okay, so this one. Let alpha not equal to 0 and putting y is equal to x by alpha in equation 4. Okay, we have minus f of x by alpha minus p minus x by alpha minus x0 less or equal to R0 less or equal to minus f of x by alpha plus p x by alpha plus x0 for all x belonging to M. Okay, because here we replace y by x by alpha for all x belonging to M. If alpha greater than 0, then the right hand side of inequality in 5 gives R0 less or equal to minus 1 upon alpha fx because f is linear plus 1 upon alpha p x plus alpha x0. Okay, because here the condition p alpha x is equal to alpha px for alpha greater or equal to 0. This implies that by cross multiplication, by alpha r0 less or equal to minus fx plus p of x plus alpha x0. Okay, so this can be written as fx plus alpha r0 less or equal to p of x plus alpha x0. Okay, so this is f of x plus alpha r0. So this can be written as f0 x plus alpha x0. Okay, here x belonging to m and x0 belonging to L minus m. So this inequality can be written as this one for m0. Okay, and if alpha less than 0, then left hand inequality of 5, this one. Okay, so r0 greater than minus f of x by alpha minus p of minus x by alpha minus x0. Okay, this can be written as minus f of x by alpha minus p of minus 1 by alpha x plus alpha x0. Okay, here common minus 1 by alpha. Clear? So here this can be written as minus 1 by alpha fx because f is linear. Minus 1 by alpha p of x plus alpha x0. Okay, because minus 1 by alpha greater than 0. Okay, since here alpha less than 0 and again with minus sign, that is minus 1 by alpha greater than 0, and applying the property p alpha x equal to alpha px for alpha greater or equal to 0. So we can write this one. Okay, so minus minus plus, so we can write minus 1 by alpha fx plus 1 by alpha p of x plus x0. Okay, so we now multiply both sides of this inequality by alpha. Since alpha less than 0, the inequality will be reversed. Okay, so this can be written as alpha r0 plus fx less or equal to p of x plus alpha x0. Okay, so again here r0 is f0 of x0. Okay, and here fx x belonging to m. So for m0, this implies that f0 of x plus alpha x0 less or equal to p of x plus alpha x0, because here we can write from this. Thus when alpha not equal to 0, we obtain f0 x plus alpha x0 less or equal to p of x plus alpha x0. Okay, that is f0 omega, x plus alpha x0 is omega. So f0 omega less or equal to p of omega for all omega belonging to m0. Thus f0 is real linear functional on m0 such that f0x equal to fx for all x belonging to m, and f0 omega less or equal to p omega for all omega belonging to m0. If m0 is equal to L, then we get the generalized Hahn-Banach theorem. If it is not so, we have to repeat the process of the extension. It is at this point that Jones lemma is needed. Let P denote the set of all ordered pairs m lambda, f lambda, where f lambda is an extension of f to the subspace. M lambda is a superset of M. That is, M lambda is the subspace containing M. And f lambda x less or equal to px for all x belonging to M lambda. Okay. Partially ordered P setting ordered pair M lambda f lambda less or equal to ordered pair M mu f mu. If and only if m lambda is subset of m mu. For f mu is equal to f lambda on m lambda. Okay. P is evidently non-empty. Let Q is equal to ordered pair mi fi be a chain, that is totally ordered set in P. Then it is easy to see that Q has an upper bound. F ordered pair of union of mi and f, where fx is equal to fix for all x belonging to mi. Since we are considering the total ordering of Q, union of mi is a subspace of L. This is true for every totally ordered subset of P. Hence, by Jones' lemma, P must contain a maximal element, order pair m bar f0. To complete the proof, we have to show that m bar is equal to L. Okay, whole space L. Suppose m bar not equal to L and m bar is subset of L. Then we can extend f0 in such a way that order pair m bar f0 less or equal to m0 bar capital F0, where m0 bar is the space spanned by m bar and x0 belonging to L minus m bar. Okay, so with this space, and f0 is extension of small f0. Since order pair m bar f0 is maximal, we must have m0 bar is equal to m bar, which contradicts the fact that m bar is subset of m0 bar strictly. Hence, our assumption that m bar not equal to L is false. So that m bar is equal to L and f0 is the extension of f on L, such that f0 x less or equal to px for all x belonging to L. This completes the proof of the generalized Hahn-Banach theorem for real linear space. Case second. Now let L be complex linear space. Okay. Here f is complex linear functional on M such that mod fx less or equal to tx for all x belonging to M. Okay, as per the hypothesis here. Okay, here f is complex linear functional. Okay, so f of x equal to, this can be written as gx plus I hx type. Okay, so gx is real part of fx and hx is imaginary part of fx. Okay, so let g is equal to real part of f, then gx less or equal to mod fx. Okay, here first part gx, so this can be less or equal to mod fx. Okay, total value mod fx, and mod fx is less or equal to px. Okay. So by case first, g can be extended to a linear functional g0 on L into R, such that g0 is equal to g on m and g0x less or equal to px for all x belonging to L. Define f0x by f0x equal to g0x minus I g0 of ix for all x belonging to L. Okay, this already discussed in the lecture 53 of Hahn-Banach theorem. f0 is linear functional on L such that f0 is equal to f on m. To complete the proof, we have to show that mod f0x less or equal to px. Let x belonging to L be arbitrary and f0x is equal to r into e to the power I theta, where r greater than 0 and theta is real. Then mod f0x equal to r. And this can be written as e to the power minus I theta into r into e to the power I theta. Okay. So e to the power minus I theta f0x. This can be written as f0 of e to the power minus I theta x, because e to the power minus I theta as a scalar. Here r equal to this one and r is real. Okay. So this is g0 of e to the power minus I theta x, because here f0x is equal to g0x plus I h0x, because f0x equal to g0x plus I h0x. Okay. So here r is real. So this is the real part. Okay. So we can write f0 of e to the power minus I theta x as g0 of e to the power minus I theta x. Okay. Again, we know that g0x less or equal to px. So this can be written as less or equal to p e to the power minus I theta x. Okay. So by equation 3 for complex linear functional, okay, here for complex linear space, p alpha x is equal to mod alpha px. Okay, so we can write this e to the power minus I theta as scalar. So this can be written as mod e to the power minus I theta into px. Mod e to the power minus I theta, that is 1. So equal to px. This completes the proof of the generalized Hahn-Banach theorem in the complex case. Corollary. We can deduce the Hahn-Banach theorem for normed linear space from the generalized Hahn-Banach theorem as follows. Let px is equal to norm of f into norm x for all x belonging to n. N is normed linear space. First note that px greater or equal to 0 for all x belonging to n, then for any xy belonging to n, we get p of x plus y equal to norm f into norm x plus y. Okay, as per this. By triangle property of norm, this can be written as less or equal to norm f into norm x plus norm y. Okay, that is this one, norm f into norm x plus norm f into norm y. Okay, So norm f into norm x, that is px. Norm f into norm y, that is py. So this implies that px plus y less or equal to px plus py. Further, p of alpha x, here it should be equal, because here px is equal to norm f norm x. So p alpha x equal to norm f into norm alpha x equal to mod alpha px. Hence P satisfies the all conditions of the generalized Hahn-Banach theorem of the complex case. Hence, applying the generalized Hahn-Banach theorem of the complex case, there exists a functional f0 defined on all n such that f0 is equal to f on m. Okay, m is a subspace of n, and mod f0 x less or equal to px equal to norm of f norm of x as given here for all x belonging to n. This implies that norm f0 less or equal to norm f, okay, by definition of bounded linear functional by dividing this one, okay, because we know that norm f0 equal to supremum of mod f0 x upon norm of x such that x belonging to n. Okay, so by dividing this by norm x, we get norm f0, and right side this is norm f. Since f0 is the extension of f from the subspace M, we get norm f less or equal to norm f0. Hence, we get norm f0 is equal to norm f. This completes the proof of the theorem. For example, let x equal to r square. P such that x to r defined by p x1 x2 is equal to under root x1 square plus x2 square. Okay. M is a subspace defined x1 x2 belonging to r square, where x2 is equal to 0, and functional defined on M as f such that m to r defined by f of x1 0 is equal to x1. Then it is clear that P is sublinear on x, f is linear on M, and fx less or equal to px. Okay, because here f x1 0 is x1 and p x1 x2 is equal to under root x1 square plus x2 square for all x belonging to M. In fact, that fx is equal to px for all x belonging to M. Here x equal to x1 x2 belonging to r square. Okay. So here for x belonging to M, that is x2 is equal to 0. So in fact, fx is equal to px. Thus, all the requirements of the above theorem are satisfied. Hence, the Hahn-Banach theorem asserts the existence of linear functional g on x, which satisfies gx is equal to fx for all x belonging to M, and gx less or equal to px for all x belonging to x. Okay, we can easily see that such functional is gx1 x2 is equal to x1. Okay, for all x belonging to M. Next theorem. If n be a normed linear space and x0 a non-zero vector in n, then there exists a functional f in n star such that f of x0 is equal to norm x0 and norm f is equal to 1. Okay? N star is set of all bounded linear functional. Okay? That is here n star equal to beta of n r beta of n c. Proof. Let M is equal to alpha x0 be the linear subspace of n spanned by x0. Define f0 on M by f0 of alpha x0 is equal to alpha norm x0. First we show that f0 is functional on M with norm f0 is equal to 1. Okay, as per this assumption, first we have to prove f0 is linear and bounded, and then this one. So let us prove f0 is linear. Let y1, y2 belonging to M, so that y1 is equal to alpha x0, y2 is equal to beta x0. For some scalars alpha and beta, if gamma delta are any scalars, then f0 of gamma y1 plus delta y2. We are putting the value of y1 and y2. Okay. So f0 of gamma y1 plus delta y2 written as f0 of gamma alpha x0 plus delta beta x0. Okay. So here x0 common. So this can be written as f0 of gamma alpha plus delta beta into x0. Okay. As per the definition of f0, this can be written as gamma alpha plus delta beta into norm x0. Okay. Again, we can write this as gamma alpha into norm x0 plus delta beta into norm x0 equal to gamma into f0 alpha x0, okay, by this plus delta f0 beta x0. Alpha x0 is y1, beta x0 is y2. So this as gamma f0 of y1 plus delta f0 of y2. So f0 gamma y1 plus delta y2 is equal to gamma f0 y1 plus delta f0 y2. This shows that f0 is linear. f0 is bounded. Let y is equal to alpha x0. Alpha x0 belonging to M. So that norm y is equal to norm of alpha x0, and norm alpha x0 can be written as mod alpha norm x0. Now mod of f0 of y equal to f0 of alpha x0. Okay. So here f0 of alpha x0 is alpha into norm x0. So we can write this is mod of alpha into norm x0. Okay. Putting the value of f0 of alpha x0. Okay. So this is already norm x0. So this can be written as mod alpha norm x0. Okay. So mod alpha norm x0 is norm y. So mod f0 y equal to norm y. Hence f0 is bounded. it follows that f0 is functional on M. Okay, so it is divided by norm y both side. Okay, so using this formula for bounded linear functional, so supremum of mod f0 y upon norm y, that is norm f0. Okay, so if you divide this equation by norm y, we have norm f0 and right side is 1. Also f0 x0 is equal to norm x0 by the definition of f0 by choosing alpha is equal to 1. Okay, here. Hence, by the Hahn-Banach theorem, f0 can be extended to a norm preserving the functional f belonging to n star. So that f of x0 is equal to f0 x0. Okay, f0 x0 is norm x0. And dividing this by norm x0 and applying this definition, so we have norm f. Okay, norm f is equal to 1 and also norm f0 is equal to 1, and hence norm f is equal to norm f0 is equal to 1. In this lecture, we have discussed the sublinear functional and generalized Hahn-Banach theorem. These references have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Narsey. Second, function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.